Good afternoon, everyone. Thanks for coming. We're going to get started, so we keep up with the schedule. The presentation for today, X-ray CAD scan, a power partner in the 3D printing resolution, and I am currently with Nikon metrology. I already had the chance to introduce myself to some of you. My name is Herminso Villarraga Gomez. All right. Let me start with this question. Do you recognize this process? Any ideas? What's that? It's subtractive manufacturing. So it's a very old technology in which you take a chunk of material and you start taking material until you get your tooling. What about this one? That's additive manufacturing. So it's the opposite process. We get the material and we start stacking up. And this is an interesting one because it's one of someone back in Minnesota. It did a house in 3D printing. It's a 3D printing castle. You know, there are crazy people everywhere. So someone decided to create that. And there are some other applications from 3D manufacturing from the Journal of Quality and Technology, like the one you see, a case for a motorbike. Other more typical and common applications from the aerospace and the car industry, from the medical industry, also for stuff that go into our knees or bodies, and for the car manufacturing. Now, the other side of the story. We've got some problems. We have sometimes issues with the 3D printing processes, and then we have to check for quality. We have defects, we have parts missing, we have cracks, and also we have porosity. So that brings me to the topic of my presentation, which is quality assessment of additive manufacturing parts and processes. And before to start, I have to tell you that assessing additive manufacturing processes for quality is a little bit challenging. The reasons are, one, the parts are complex and free-form parts. Being free-form parts means that, well, it's nice. We have a lot of degrees of freedom, so you can make curves and shapes that are irregular shapes. But then it's challenging for the traditional inspection technologies that are used to circles, perfect planes, cylinders, and stuff like that, like when you use a CMM. So that's the first challenge. The second one is that it generally brings internal geometries. Internal geometries that are not easy to check with a tactile CMM or with a visual system, unless we get inside somehow with a probe to check inside of the part. Or if we destroy the part. The other issue is that we get roughness. The surfaces from the additive manufacturing parts are generally rough, which also become a challenge for a certain type of inspection technologies like a probing system, because it scraps the machine. It scraps the tooling and also the part. And the fourth one that I have for today is that sometimes we see in the inside there are powders that have not been melted and they are still in the inside. So now, who could protect us? Well, one possibility is X-ray computer tomography. And that's because we can see inside of the part without destroying it. And there are different kind of technologies from X-ray CT that go from nano resolutions to macro resolutions. The thing is that depending on the size of the part, the resolution is also limited. So you can scan big parts with CT, macro or micro CT, but when you have to scan in the nano resolutions, the limitation of the size is small. You cannot expect larger resolutions in a part like an engine block. But X-ray CT is not the only technology. There are other technologies out there like white light interferometry, which gets you the highest resolutions possible, but the thing is quite limited to just checking the surface. It needs to illuminate the part. We have eddy current and ultrasonic testing that those technologies can get in the inside somehow, not very deep, or depending of the technology, but then also it's limited by the resolutions. And then we have X-ray CT, computer tomography, with the advantage that can actually reconstruct the full volume, the interior surfaces and structures, and also the exterior surface. It has some limitations for the resolution. It's not the high resolution of a white light interferometry, but still it can get high resolutions depending on the size of the sample and the material. And the typical a typical example of X-ray CT is right here. If you look at this blue plane, it's coming from the top and going back down without destroying the part, and you can see all the bonding and the interlayer and the powder that goes from one structure to the other. So this is a very good example that gives you a lot of the inside of what's going on in a finished part. So yes, X-ray CT is a powerful partner in the 3D printing resolution, and I'm going to show you some other cases. Before that, I'm going to tell you who we are, because Nikon specializes in metrology equipment. We are located very nearby from here, like half an hour by car, and you can visit us if you want. It's a very nice weather out there. It's close to summer, and take advantage of that, because the most typical scenario around here is something like that. So we are specialized in small snow removal, of course. So that's what we do. And again, I have to clarify that we are in this business because when people hear about Nikon, they generally think about cameras. We are a company that are very known for cameras. But we do optics for metrology, too. We do laser scanning, multi-sensors for CMM, laser radar, video measuring microscopes, and X-ray CT, which is the topic of my presentation today. So please smile. This is a typical X-ray or radiography, 2D, but we can actually, with computer tomography, get into the inside of the part without destroying and create all the surfaces inside. So that's computer tomography. We have been in the X-ray CT business for over 30 years with more than 3,000 CT systems installed worldwide. So we have quite a lot of experience in this. The company is more than 100 years old. And this is another example that now is going to check for porosity. So you see, this is a casting, but it applies also for additive manufacturing. You can go inside, see all the cross sections, check for the porosity of the parts, or if you have any cracks, you could check for that as well. And not only that, it's not only visual, but it's quantitative. You can make a calculation to calculate the volume of each one of those voids and create a porosity map and create a scale. So the blue ones are very small voids, but a lot of them. And then when you get the biggest one, the red one, on the other end, then you have volumes of 87 and 8 millimeters cube. So that's what we do, X-ray and CT technologies. Again, X-ray, a simple radiography doesn't tell you all of what is happening, because even if you see some porosity from the radiography, you don't know exactly where it is, and you cannot calculate the volume. So the computer tomography actually brings the next step. Why 2D radiography is not enough? For some application it might be, but not always, because sometimes it's ambiguous. Do you see that image? What do you think is that? A hand, right? Well, it's actually a bunny trying to be funny. So the two approach is misleading sometimes. That's why we need to do the full X-ray-CT. How the technology works? Well, I'm sure you have gone to the doctor or hear of someone going to the doctor where they say, well, you have something fractured in your bone, and they say, we need to do a CAT scan. So they put you inside of a machine, and they rotate the machine around you while you pass across, and they get a 3D map of your bones. The industrial case is exactly the same. You have X-ray source, and you have the detector. The difference is we keep these objects stationary, and we have a rotating table to rotate the part. So the part rotates around. Why don't we do that in the medical system? Well, it will be very annoying to put the patient to rotate around the machine. So we do that, but for mechanical parts, not for patients. And this is a typical system. I want to show you the full workflow of measuring. So you collect several radiographs or projections at 360-degree rotations. You collect in the order of 1,000 or more projections. And with those projections, then you, using a software reconstruction, then create a volume. Once you have the volume, if you make an accurate surface determination, you can actually take measurements, do metrology, tolerance, geometrics, and tolerancing verification. So that's industrial X-ray CT. That is also used for metrology or for non-destructive inspection, checking for voids, porosity, and part to CAD. You could bring the CAD and compare against the scan and see what are the deviations in a color map. Of course, because that image, you might be wondering, what is that CAD doing there? Well, a lot of people wonder that, and the answer is, well, CAD is computer axial or aided tomography, so CAT scan. And that's actually my cat. But I have to make a little warning of caution, so don't put the cat inside of the machine. My wife will kill me if I do that. And please avoid misunderstanding. I say CAT scan is not just to put it in the photo scanner. So that is quality measuring with CAT scan, different types of applications. And I have one example here, one that we did with internal cavities. This is the sample, that's the CAD model. And when we scan the part, then you see the transparency. But when we overlay the CAD part, the design, against the scan, then we can see a map of deviation. That's an interesting map of deviations because it not only tells us in the actual part, but it can give us a histogram with the typical deviations, which you see that are up to 150 micrometers in this case. You should check also for porosity, but also in some cases for channels that should be open, and some cases are just blocked by the powder melting right there. And the porosity map, in which you do the calculation, and you have the porosity with different colors, but it gives you a histogram with the volume and a numerical count of the quantity of voids that you have in there. One more application, checking for flexures, that they are actually straight, that it should be. They are not in this case. And if you improve your process from additive manufacturing 1 to additive manufacturing 2, then you get improvement. And you can check that with the part to CAD compare. You see that process 2 is much better, but still there are things missing at the corners. We all know that the corners are very challenging for this type of technologies. Oh, and the porosity calculation. By the way, I am using volume graphics for using these calculations, which is a software that is almost standard for doing these computations. So you have the porosity map for process 1 and process 2. You can compare and choose which one is a better process for you. Now, when you check for porosity, one thing that is very important is the resolution of the scan. So I have the same part scanned with a voxel size of 32 micrometers and one with just 12. And you see that improving the resolution not only allows you to see the voids, you see the voids here, but you see them better. And not only that, you start seeing more pores popping up that you were not able to see before. And you get the idea. If you have an additive manufacturing process, then you have to do metrology inspection or quality control. Then if there is something that is not working well, then you do a process of optimization, the enhancement of the design, do the process again, check for inspection until you finally get a good product. That's for checking the parts. But what about the powders? Have you ever checked the powders? Well, this is an X-ray CT scan of powders, 2 different powders. And there are 2 interesting things here. This is Inconel, very popular, and that's aluminum. So you see why people tend to like a lot Inconel. The particles are quite round and homogeneous inside. They are not perfectly spheres, but they are very round, very close to spheres. While in the aluminum powder, you have very irregular shapes. They look more like, I don't know, potatoes. And you see voids inside, big voids. And you also see some voids here in the Inconel powder. So that's very necessary to check your powder so you don't get implosion on the generation of the 3D part. And this is an example of porosity calculation on a turbine blade. In collaboration with the Case Western Reserve University, you see the porosity map there, and you see actually a video here where the porosity is concentrating. Again, this is just a research project. Don't worry about, we're not putting those turbine blades in airplanes, so this is still safe to fly. And we do also projects in collaboration with the National Institute of the Standards in Technology and Technology, creating parts with voids that we actually make them and see if the machine is able to create those perfect spheres. When we scan in the X-ray CT, we see that is not the case. The spheres are not actually spheres. They are a little flat on top. And that color map tells you the deviation. If we change the design from spheres to square to cubes, then you see the same effect. And only when you change the design to a tilt kind of cube, then you get an improved design for optimization. There are other applications that you could do with X-ray CT data for additive manufacturing. And I'm going to give some projects here that we do research in collaboration with other institutions. This is a truss bar for the spine, your back spine from Fort Webb Medical. So you have the manufactured part, you scan the part, you get the mesh creation of the volume with simple wear, and then you could do a simulation, applying forces to that data. And you could take the same thing with your CAD model as designed and compare the simulation from as manufactured and as designed. And here is a little video of more or less what you do in simpleware using the CT data. And that's the data and how the forces are going to be applied on the top and the bottom. And also we have collaboration from Thornton and Tomasetti company. And the results are right here. So you have as designed and as manufactured, and you see there are some little bit of differences, although the trend or the behavior seems to be the same. So it means that the actual CT data can help us to get an insight of this kind of testing. And that's not the only companies or people that do that. We have Carbon 3D, one of our customers, use our systems for getting the CT data and getting also comparisons between process A and B and see how it works. For tensile testing and also for wall thicknesses. So what you see here is a calculation of how thick are the walls of that part. And you see for process A and process B, what is the difference between them in terms of fractions of per volume. Our friends from the Johns Hopkins Applied Physics Laboratory also do this kind of test for wall thickness analysis, and they have another interesting one for checking linking porosity to failure of the additive manufacturing parts. This is another one which is quite novel, because usually the computer tomography is known to help with volume analysis, not for surface analysis. For surface analysis, you'd use other technologies. But, well, our friends at the UK, collaborators with our company and other university at Italy, has been dealing with this project, which is extract actual surface data from CT data and compare against another reference systems. And this is the surface that we get. And when you get the comparison between the CT data, which is over there, against the visual system, for example, the Alicona system, you see that is very reliable. They compare well. So that's some of the novelties that we are doing with additive manufacturing characterization. And there is another university in Italy that is doing the same, University of Padua, and this is a profile of the surface extracted by CT with a reference and a confocal system. So the article is already in press, but you could also already see it online if you want. So what can you do with X-ray CT? You can scan in reality a lot of parts, and there are different systems capabilities for different parts. For small parts, you can use systems that give you a power less than 160 kV, no problem. But if you increase the dimension of the part, of the density of the material, you have to start using 225, 450 kV or up. And the advantage that we have, at least Nikon, we are proud of it, is that we are the company that offers the largest rank and the only manufacturer in the market that offer microfocus CT systems in the 450 range. The microfocus is very important. That's the size of the focal spot where the X-rays are being generated. And if that focal spot grows, then there are limitations in the resolution. So it's very important to keep that in the microfocus range if you can, and scan stuff like this, which is 50 millimeters diameter, and it's an Inconel part. You can visit us. We are in booth 716. We have different systems that go from 160 to 450 and walk-in rooms. So those are some examples that you can see of different configurations. And we can scan different size of parts. I always tell to our friends and customers that we can scan stuff that is as small as the head of a pin or as big as an engine block. And we do for the engine blocks with systems that are called walk-in rooms, where you can actually fit yourself and fit in there 3 different X-ray sources, 225, 320, and 450, and 2 different detectors, planar and linear. And we do that with help of a company that is Avonix Imaging, which work with us creating the manipulators. We give the sources and the detectors. So to summarize the measurement process with X-ray CT, when you have a part that you want to inspect, you have to think a little bit how big is the size of the part, what is the size of the part, what is the type of material, set the machine with some scan parameters, turn on the X-ray, take projections. With those projections, then we can reconstruct a volume. Generally, the non-destructive testing people stop here because they just want to see porosity or if there is any cracks or defects inside. But this technology can be used also for metrology, which means you can check tolerances. So you do a strategy of measurement very similar to a CMM, and then you give a report. So I think I have talked enough for today. I'm going to just give quick conclusions. Well, imagine you can see inside. It's a big advantage. And there are different types of applications. Casting for void analysis, additive manufacturing, void and dimensional analysis, electronic inspections, porosity, fiber analysis, dimensional metrology, but not only manufacturing, also the rock exploring or fossils, all kind of stuff in biology too. Where we are at today. The discovery of X-rays happened in 1895, and since then, the medical industry discovered its potential and started using it for checking what is inside of your head or in your bones and see what is wrong. And that was typically just X-ray, radiography. But in 1971, a little more than 30 years already, the first CT scan was created. The applications for the medical industry were follow up after that. But also the non-destructive inspection for checking for cracks, porosity, and electronics components. Since around 2000, we have been using it for dimensional metrology, geometric and tolerancing analysis. And we do today very accurate inspection of metrology with X-ray CT systems, and also additive manufacturing, inspection of 3D printed parts or additive manufacturing. With radiography, the new trend is to do also in situ imaging. This is a laser melting some powder, and you can see in real time what is happening in there. How is the different layers being created? And if I go to the next one, you can see a lot of the dynamics that is happening inside of melting this powder. If you are interested, this is an article that came in Nature Communications very recently, this past year, and it's free access. You can read it there. So that brings me to the end. I just have to give acknowledgements to my company, of course, but not only that, but also to all the collaborators, which the list is quite large, but I'm going to mention just institutions, to Avonics Imaging, Volume Graphics, Case Western Reserve University, NIST, Synopsys, for Web Medical, Thornton Tomasetti, Carbon 3D, John Hopkins Applied Laboratory, UK Collaborative Group, University of Nottingham, National Physical Laboratory, Huntsville University, University of Padua, and of course, all of our customers. With all the I always say that I'm basically standing on the shoulders of giants, which is literally true, as you can see from the picture. With this, if you have any questions, I'll be very happy to answer. Thank you very much. Questions? Yes, please. Just take the mic.
Can you speak to using CT in volume production?
Yes. So that's the other trend that is coming up. Is we use robot that can load the part and scan the part in production. We have some examples. If you stop by my booth, I can relate you with some of those examples and show some videos how we do that. You have to automatically, have the parts passing across a robot that picks up the sample, scan the part, and then get the analysis, and then discard or keep the part going, and you do production with that. The challenging thing with this is, can we do it faster? Yes, but it depends on the application. The bigger parts and high density, you need to scan with more power, and it takes more time. But as as long as you are interested in a quick scan, quick inspection, with some not very big samples, you can do that. You can perfectly do that. We have a couple of examples, customers of us, that you invest lines, and they don't care about much the accuracy of the reconstruction. They just want to get the scan and get an STL to go and print it. And they can do that under 1 minute. And they do thousands of parts like that. We have 2 examples and others more in the plastic industry. Any other questions?
You mentioned you can do engine blocks. Are you able to do larger objects, say a prefabricated housing module?
Can you repeat, please?
The ability to use X-rays for large objects, like a full-size building module.
The largest part that we have scanned is like kind of an engine block. So that's the kind of largest part. You could do larger, but you have to get a different type of sources. I have seen people doing it in some places in Europe, scanning a full car, an actual automotive car, but takes several days, and you have to create a special room for that. It's possible. It's just challenging, because one thing of the physics of the X-ray is there are 2 things that start, it has an exponential decay when it passes through the part. So there are 2 things that limit the pass of the X-rays to the detector. One, the distance. As the distance starts increasing in the sample, the X-ray intensity starts decreasing. And the other thing is the material. If the material is plastic, no problem. You can pass with X-rays, no problem, unless it's a very, very, very large part. But if you have stuff like nickel alloys and stuff like that, then your part start being limited to small parts, because it's, the atomic number is higher and the X-rays get stopped in the way. So it's a problem of density and size, yes.
Hi, have you guys used this on any 3D printed biomaterials or bioscaffolds?
We did, I don't know if you saw the example from for Web Medical. Let me go back. But that's one example that people use it, and also for when they insert stuff in your knees for helping the growing of your bones. That also can be done. I'm very close there. One more, that one. That one. So that's a medical part. This go into the spine of your bone. It's a medical application. And from seeing the part, you know that it has a high rugosity, which is designed like that to help grow of your bone around the part.
But with any biomaterials, so that's metal.
Yeah, no, not that we have scanned that, but if you have one part, we can talk.
Okay, thank you.
We might be able to do that. I mean, I have gone customers that bring with me the part already inside of a bone and in a liquid, and we have to scan that to see how much of the bone has grown around the part. And so we have done that. So to calculate the volume of growth inside of the part for your knees or for your bones. Any other questions?
Thank you so much for your presentation. So a lot of the scanning is after the printing is done, correct?
Yes.
So is there maybe in the future, or if it's already out, to scan while it's printing, to notice the defect as soon as it happens and stop the print? Or
Yes. The video I showed you, it was inside inspection with just radiography. You can get an inside. For scanning the part, you could do that if you design your system and you put it inside of the machine. It has to be shielded against the X-rays, so you have to do the printing inside of the machine. And as long as the process is slow enough, so when you go at 360 degrees rotation, then you can see the change. So what you do is several scans. And we have done it not for this specific application, but for the grow or biological seeds. So we plant the seed because the grow is slow, then it gives us time to scan, it grows a little bit, scan again, and it keeps scanning 72 hours, and then after that you can create a video. And we call that 4D scanning because you have the 3 dimensions and the 4 dimension, which is time. So yes, it's doable. It requires some adaptation. And the 3D printing to be slow enough to go 360 degree and keep checking.
If you want to come back tomorrow, I'm having a talk at 12:20. I'm volume graphics, so many of the things he's talking about with regards to volume graphics, I'll be talking about that and additive manufacturing tomorrow at 12:20. I invite you folks to bring back your questions again tomorrow as well.
So he's basically advertising his talk for tomorrow. Any other questions? Well, if there are no more questions, feel free to stop by our booth. You can talk to us, and thank you very much for coming and listen to this presentation. Thank you.